And greetings, everyone. You can tell I'm a little rushed. Dr. Russell Humphreys will be joining this channel in about 2 hours on a different stream. I segmented the streams apart so that they don't run over each other, and it's easy to find what Russell Humphreys has to say. I'll be monitoring my phone in case Dr. Humphreys calls. If there are any technical issues or whatever, this will be the first time that he's going to be using StreamYard. Our last meeting was through Zoom. So what I plan to do in this stream is to just keep reading through his paper. I had discontinued reading this paper briefly for two reasons. One, I got to the point that I said it would be counterproductive for me to keep reading through the paper and not understand what it's saying. And I said it'd be good if I could talk to Russell Humphreys for him to clarify the terms. And it'd be great that it's recorded, and then I could also just verify my understanding, because he could say one thing, I need to be able to reference what the pointers he gave. So this is great that it's being recorded. He's actually going to explain the mechanics of the paper like one would to a physicist or an electrical engineer or electrical engineer. Because we're dealing with lots of, this is full of electricity and magnetism, guys. So, electrical engineering has its specialties. You have the guys that really do deal with magnetism and electricity. And then there are the guys that are just pure electricity and just circuits. Or they're building VLSI systems, or if they're like Menrex, they're working with lasers and photonics. There's so many specialties. Then you got the computer guys in electrical engineering. They do a lot of hardware architectures. Everyone has their specialty. So antenna engineering uses a lot of electromagnetism. This is a specialized application for electromagnetism. So this is definitely one field that it's good to either be a physicist, have physics background or electrical engineering background. And as you could see from some of my nerd torture sessions on multivariate calculus, to just as a preliminary to understanding Maxwell's equations, this is not, this takes a little thought. Not for those who have hearts that are faint or minds that are made of pudding. So that's just a mean joke. I'm just gonna read through this paper, and I'm gonna take notes and say, Dr. Humphreys, let me understand this term correctly, this concept that I'm stating it correctly. He'll use terms like colloidal and azimuthal. I'm like, okay. And so we're probably going to go through maybe 2 or 3 pages of his paper. Maybe then I'm going to go back and read up until this point, and then maybe we reconvene in a month after I've struggled through all this. The importance of this topic, glory and honor to our Lord and Savior. Lord, I meant to acknowledge you in all my ways here. The importance of the topic is that if the geomagnetic field is decaying as fast as we think, it would strongly suggest the Earth is young. Wikipedia, let me just point this out, just to set this up, guys. Let's see, let me show. Wikipedia, geomagnetism. How did I get a Spanish version of this? Is it because my name's Salvador? It thought I'm wanting this in Spanish? I can sort of speak Spanish. Wait, that's Microsoft Bing, not Google. Ugh. Geomagnetism. See, I got a new computer and some of the settings I need to get it to default to what I'm used to. So I'm looking at geomagnetic field. Earth's magnetic field, Wikipedia entry, okay. All right. I got it, guys. Hang on. You could tell that these shows are definitely not scripted. I'm just doing them on the fly. You know, what comes up in my mind, I start to explore. So there's a Wikipedia entry on Earth's magnetic field. And let me search on the word 1600. So we have this graph the dipole strength in microteslas. I have to actually do a part of a show on what a Tesla is, the unit. Let's try to see it in terms of what a Tesla is. Hang on. I want to look at what this means. What is a Tesla? And I don't mean the car Tesla by Elon Musk. Let's see what a Tesla is. A Tesla is the unit of the magnetic field strength. And it is kilograms per second squared times amperes. So kilograms the mass. So this would correspond to, like, if you had certain number of amperes per ampere. So as you throw in more amperes into the system, you can influence more weight. So actually, some ways that we measure magnetic field strength is with kind of like a scale. And so if you have a strong magnetic, I mean, you can kind of feel it. You have strong magnets, it's harder to pull apart. So the magnetic field strength can be kind of measured by, the strength of the pull, plus some other things like the current being pumped through. But that's roughly, this is actually good that we can relate it to like kilograms, the amount of kilograms being pulled. That's not really right, okay, but this is close enough. So you see it there, it's kilograms per second squared per ampere. Kilograms per second squared per ampere. And measuring magnetic field strength. Using a, let's see, scale. See if they have anything. So they have field strength measurements like this. This is for really powerful magnets. You could just use a scale, and that would translate, I presume, into Teslas. I mean, these are really powerful, but if you want something really sensitive, you get a field strength meter that's constructed differently. So, I mean, just for completeness, I wanted to visit that topic. So the field strength, we actually started measuring in 1900 with precise methods. These dotted lines are inferred here. And let me verify that. But this again is relating to IGRF 12. Do they explain how it was measured? Okay, so some of this was done with models, and some of it was inferred. Okay, this is interesting. The GUFM model estimates back to the year 1590 using ship's logs. So I guess there were compass. There are probably a lot of compass measurements. So the direct measurement that can be done, but the rest is you're going back in the logs of these mariners, and you're going to try to figure out the strength of the magnetic field. Okay, there's some, it's not a direct measurement. So I just need to point, this is a great graph here. So the geomagnetic field, 1616. So we had some models. We had some models. But I want you to see that from this dotted line here is still inferred, it's models. The blue line is actual measurements. So that looks like to me 1900, 2000. So maybe a little over, about 120 years of actual measurements of the field. And then we have some that are kind of inferred using ship's logs. And that would be the GUF M1. Okay, GUF M1. GUF M1. That said they could go it to 1590. And then paleomagnetic research produced models dating back to 10,000 BC. Okay, maybe. I have to question that. Because could be circular reasoning. If you're assuming the Earth is old anyway, it will affect your model. So I like the IGRF. For historical data about the main field, the IGRF may be used back to the year 1900. So let's look at IGRF. International Association of Geomagnetism and Aeronomy Aeronami maintains a standard global field model called the IGRF, using data from satellite. The 11th generation uses data from satellites. I don't know where they got the earlier ones from 1900. All right. But I would say we could definitely model it. I mean, we could definitely measure it for about the last 120 years. So I need to point out, when you look at that graph, it says here, at this rate of decrease, the field would be negligible in about 1600 years. Now they said here, however, the strength is about average for the last 7,000 years, and the current rate of change is not that unusual. And I pointed this out before. That second sentence, that final sentence, is circular reasoning. We don't absolutely know. We don't have direct measurements from 7,000 years. That's an inference. And that's that other model that they're using. So let's see, let's go back to IGRF. Yeah, the paleomagnetic model. Just throw it out, guys. It's not a direct measurement. I'm sorry. It's not a direct measurement, and it's based on an old Earth assumption. Oh, Mark O'Connell said, and I found the paper online. Oh, thank you. Greetings, Mark. Thanks for all your support of the channel and your interest. I'm just saying, when we give these figures, we have to distinguish with what we actually measured and when. And we've actually, as far as I could tell, for the last 120 years, we actually have real measurements. Anything that goes back 7,000 years is suspect if it's a paleomagnetic model. I'm sorry. Same for millions of years ago. You know, it assumes the very thing we're arguing about and that we're trying to prove or disprove. It's assuming it is true, and that's not helpful. So if we even just extrapolate, okay, let's extrapolate this graph here. You want to use a linear or exponential model. Wikipedia is saying at this rate of decline right here, so the blue line is real measured data. If this continues, there's not going to be any magnetic field. This suggests that the magnetic field is recent for the reason that it would have to be absurdly strong millions or billions of years ago. And that change in the magnetic field, there's a lot of energy release associated with that. It would make the Earth molten. Not to mention, how can you get a magnetic field that strong? So just bringing up again the relevance of why we're exploring that this could be a very good evidence for a young Earth. And it also has consequences for, hang on. If you saw the picture of the pretty girl, that was from the earlier talk I did on the curl. And when you search for curl, you get all these pictures of girls with hair curled. And the curl is an operator in electromagnetic theory. So anyway, I can get rid of that. Let's go back to see if I can go back to the paper. All right, so we're going to go to Russell Humphrey's paper now. Planetary Magnetic Dynamo Theory. And we're just going to read. So now we have the importance of this, and we're just going to slug it out through this paper. And then Dr. Humphreys will be joining us on this channel, but in another stream at about 3 o'clock. You will be talking about this paper, which he presented in 2013. So we have these dynamo theorems. We've covered that in the first 5 parts. This is figure 6. I'll ask Dr. Humphreys about figure 6. Amperes per meter squared. Okay, so I'll ask him briefly about figure 6. This figure 6 looks like the one in Wikipedia. And I'll ask him about the Wikipedia figure of 1600 years. All right. So I'm going to just keep going through. We covered this barely. This is an interesting equation. So I'll ask him about equation 2 and 3b. I mean, how many? Okay. The peak current density, a core radius of the core radius with the magnitude about 0.6 milliamperes per square meter, right here. Milliamperes per square meter. So your pen light battery, your AA battery probably can generate like easily that amount of current per square meter. Yeah, it could power that. But remember, the Earth is a very large surface. I mean, bazillion square meters. All right, so let's just keep going. So now he's describing, okay, the dipole field. He's describing so this is equation 4AB. I'm going to look at this. Equation 4AB. I might ask Russell Humphreys. This is where the geometry of electromagnetic theory gets kind of funny. B, the magnetic field is in the radial direction, and then theta. All right, so going to here, the magnetic field is pointing like that, and then also a little bit out. Yeah, that's right. You had the magnetic field. So at the points, okay, I'm seeing it now. What that equation is describing, so this equation here, all right, I'm going to try to show you a visual of the way I think of what he's trying to describe. So go back to the Tesla geomagnetic field. So that equation, let's see if I can move this out. That equation there, let me roll this up a little bit. So go to the geomagnetic field. So what can happen is, my understanding is you can generate this graph. You can kind of see this graph. This equation will generate this graph of what the field lines look like. Also their intensity, something like that. I'm just trying to relate the equations to what you're seeing on the graph. So let's go back to the equations. I'm just trying to give some meaning to all that's going on. This is telling us how quickly all this will decay. The current, what is sigma? Sigma, do I have sigma? Okay, we know what pi is. Mu naught is the magnetic permeability of free space. I don't. RC, I think, is the radius of the core, and I don't know what sigma is. Oh, the conductivity. There it is, right there. So, for electrical engineers out there, you can state resistance, or you could state it in terms. You can, I normally think of in terms of resistance. It's how, if you have a certain amount of voltage, the resistance is kind of like how much the current flow is prevented or resisted. So if you have a high resistance, even if you have a given voltage, not a lot of current can flow. A low resistance, more current can flow. You can also, instead of saying like resistance, the conductivity, and I get a little confused with conductivity. So sigma is the conductivity. You just take 1 over the resistance that you measure in ohms. All right, so this is a nice formula. This is telling us, let me see if I'm reading this right. This is telling us when the end of civilization, that figure there is when the clock really starts to tell us when the end of civilization will happen, just to kind of make this more dramatic. There it is right there. This is when it'll be evident civilization's is on its way to destruction, right here, equation 5. Let's see, I call that the end of the world equation. And for Ben Rex out there, and you electrical engineers, you're familiar with the RC time constant. There's an exponential decay. So if you have a resistor capacitor and you have a charged capacitor, and then you're going to discharge the capacitor through a resistor, if you have a high resistance, it will decay slowly. If you have low resistance, it decays quickly. And the convention is after 5 RC time constants, it's effectively dead. I mean, an exponential decay doesn't really, mathematically speaking, it asymptotically approaches 0. But, 5 RC time constants, it's going to be effectively gone. So I wonder if we plug this figure in, and do we get the Wikipedia entry to agree that 1600 years, the clock starts ticking on the end of the world. So I'll call this the end of the world equation. Okay, so we have this toroidal field theory. It is likely that the 2% westward drift mentioned in the velocity subsection above decreases with depth, and is roughly proportional to the distance from the Earth's rotational axis. This means parts of the core fluid with different depths or differential latitudes will rotate westward with different speeds relative to the solid mantle above the core. So just imagine like this ocean of current, electrical current, electrons, whatever. It's moving faster. The current flow is faster at the equator, at the surface of the Earth and the equator. But as you get closer in, I mean, it's faster at the equator than, like, say, up here toward the North Pole. It's faster not just tangentially, but also in terms of omega. I think that's right. And that will cause these lines, and I think these are what they call palladial lines. And that's what I'm going to have to ask Dr. Humphreys. Okay, so, all right. Let's read. It's figure 10, the omega effect in the Earth's core. Different rotation speeds of fluid twist the palladial flux, right-hand side. So if we didn't have this differential speed in the currents, in the flowing currents, so this is what I'm going to ask Dr. Humphreys. What is actually moving? Okay, so figure 10. Are they saying that the Earth's the liquid mantle, there's more physical movement at the equator, that kind of this liquid iron is moving about faster? What is moving? Is it liquid? I'm just going to ask him, is this liquid iron moving faster? And what that would do is, if we didn't have the differential speeds, you get magnetic lines that look like this. Instead, we have these kind of, I think that's called sheared. Okay. Now this is starting to knock me out. This differential rotation has a significant effect on the magnetic fields in the core. Alf Venn was a Nobel Prize winner, I think, in plasma physics. Alf Venn's frozen flux theorem, by the way, Alf Venn rejected the Big Bang, just FYI. Nobel Prize winner. Alf Venn's frozen flux theorem, well known in magnetohydrodynamics, says that flows in an electrically conductive fluid will tend to carry the lines of magnetic flux along with it, just as if the lines were streaks of dye in the fluid. Oh yeah, and plasma physics was not one of my funner classes. You have all these charges moving in a plasma, and you have to model what the magnetic field looks like. Anyway, so magnetohydrodynamics were streaks of dye in the fluid. Flows parallel to the lines have no effect, but flows perpendicular to the lines do move them. So differential rotation in the core will shear palladial flux, north-south lines lying on the meridian plane, as do the dipole flux in the east-west or azimuthal direction, as figure 10 shows. And perhaps looking at Jupiter would help, as it visually shows the different movement areas. Yes, agreed. Good one, Mark. Good one. The shearing stretches the lines of force as if they were rubber bands with some tension, adding to their intensity and energy. The result of continued shearing is a set of toroidal lines of force, magnetic flux in the azimuthal direction. Dynamo theorists call this the omega effect. It is a robust phenomenon verified by laboratory experiments and the observation of the sun's surface magnetic fields. For later discussion, it is important to notice that because Earth's rotation generates this toroidal flux, it is necessarily symmetric around the rotation axis of the Earth, not around the magnetic axis, which tilts 11.5 degrees away from it. So there's probably some toroidal field, magnetic field in the core, and it is very important to dynamo theory. We can make a rough estimate of the strength as follows. First, notice that the westward drift of small magnetic features at the surface of the core will make one full revolution every 1800 years. Each revolution will add at most one turn to the toroidal flux, less for the interior, which has slower drift. Second, note that the toroidal flux left to itself will decay freely, just as the Earth's dipole flux appears to do. It turns out that the slowest decay mode for toroidal flux is about twice as fast as the slowest dipole decay mode. The ratio of decay times is T toroidal over T dipole. Oh boy. This is just killing me, guys. T, that's what I call the doomsday equation. So let's go back up to when the end of the world is signaled. Let's go back up to ooh, this is painful, guys. So we showed this, I call that the doomsday equation, equation 5. You actually have two doomsday clocks going. There is the clock associated with the toroidal field. So I'm going to have to ask again, what is that toroidal field? So we have that toroidal field, which this is what I'm going to ask Dr. Humphreys. So we have a globe. And is he saying that inside the core, you have all this liquid iron circulating around? And like Mark pointed out, it would look kind of like the planet Jupiter, where you have a lot of speed at the equator and not so much toward the pole. And does that generate the toroidal field? So we have a toroidal field, and then we have this other kind of field. Holy smokes. It's the dipole field. What is a dipole field? Is that because the Earth's rotating? Does that create the dipole field? Now I'm confused. So you have a toroidal field and then you have a dipole field. And I have to ask Dr. Hunt. This is why it's great to have the expert kind of explaining this. In all honesty, it's so much easier to read biology papers because it's not like doing this physics stuff where you have to have so many preliminaries just to be able to, and they're hard just to get to where you could understand the paper. There are a lot of biology papers that you can actually get through without having to dig and crawl. I mean, I remember I did not need as much, hand holding and spoon feeding to learn biology and some of the, even the biochemistry and organic chemistry. But this physics stuff, you have all these equations, and you could see where it struggles. It's like, well, what does that equation mean in relation to this globe? And you're just kind of like knocking your head. And so that's why I'm really grateful Dr. Humphreys for his time. So I have to ask, what's the difference between the toroidal field and the dipole? Okay, see, this is good. So Mark says, I think it is the charge in the mantle creating the dipole field, the direction of current. So these are going to be great questions. So you have a doomsday equation for the toroidal field and then the dipole field, and I think, do the two combine? So I'm going to ask, do the two combine? Do you take the dipole field plus the toroidal field? I mean, this is going to be, is he saying, I mean, I got to ask him this. So just, you have the globe here, and then let me just try to get the camera going here. So you have the globe here, and you can imagine this toroidal field, and the magnetic field is a little off axis. Let me tilt this. So there's Canada there. So the magnetic field, I'm sorry, the magnetic field is tilted 11 degrees. I'm doing it 45 just to exaggerate. Is he saying that the Earth's core is not, the Earth's mantle is rotating differently than its actual spin? I mean, do we have a, the net spin of the Earth's, not mantle, but the core? That liquid core is actually kind of not spinning on the same axis as the Earth's rotation, because we obviously have a magnetic north, and Mark O'Connell's a pilot. He knows this. Magnetic north is not the same as geographic north. Magnetic north, so this is Canada here. Magnetic north is somewhere around right there, not at the geographical North Pole. And I think Dr. Humphreys is pointing out some of the issues with that. Okay. I think after about 15 more minutes of this, I need to take a break. My poor brain is overheated. We were spending time on earlier in the day on the curl operator, what I call the girl curl operator, and now I'm kind of getting burned out a little bit here. Plus, I got a very stressful call, not very, in the middle of my last stream. So, all right, so I think it's simply the direction electric current within the mantle that creates the dipole field. So the Earth's direction is from east to west, if memory serves me right. So, let's just have our ideas, and then we'll compare and contrast them with what Dr. Humphreys says. So, and then I'll always ask, I say, okay, Dr. Humphreys, is this the mainstream view or is this your view? And I think for a lot of what he's saying up until this point, a lot of this is mainstream stuff. Yeah, the right-hand rule. Oh boy. This is where this is why electromagnetic theory is so hard. You're doing things in 3 dimension. You got the math and then also kind of conceptualizing. And you're trying to imagine these field lines and their intensity. The magnetic field, electric field is easy to understand. The magnetic field is, with all the curling and circulation, it's just, I do know professional physicists like to avoid, I mean, they deal with magnetic fields, but the math is just nasty math compared to electric field, which is kind of straight up, because the magnetic field has all these circulations in it. The electric field's kind of just straight up. So, okay, anyway, enough of me complaining. So we have these poloidal and toroidal. Poloidal and toroidal. Using the observed dipole decay time for the Earth of 1611 years, captioned in Figure 6, gives us a toroidal decay time of 788 years. So while it takes at least 1,800 years to wind up the toroidal flux by one turn, in the same period, the toroidal flux has gone through several exponential decay times worth of decay, taking away from the effect of the winding. The number of turns that remains in effect in the toroidal flux roughly indicates the enhancement factor over the poloidal field intensity. So an upper limit on the ratio of the toroidal field to poloidal north is 0.44. The dipole poloidal field is the highest near the center, but differential rotation is low. The shear increases with radius as we move outward, but the field also decreases. The two are both significant levels near the middle of the fluid core. Using the dipole field in that region of about 750 microteslas, we can say that the toroidal field is less than 300 microteslas or 3 Gauss throughout the core. Near the top of the core, the toroidal field, which should diminish with radius, is probably 100 microteslas. Okay, guys, I need to get a little coffee. I'm getting hoarse. And maybe I'll read one more paragraph and just let it rest at this point because I'm so confused. I don't think it would be productive to remain in a state of confusion and just keep reading through this. I need to know what a poloidal field and what creates it, and what's a toroidal field and what creates it. And do you just sum the two fields up and then you come up with something? This is killing me. And Mark, thank you for joining us, brother. God bless you, and thanks for your interest and your support of this channel. Very much appreciated, sir. All right. So this is page, I don't have a page number here. All right. So now, actually, why don't I read the paragraph? I don't understand it. We'll just read it, okay? So a lot of learning is just sometimes reading stuff you don't understand. Maybe later you'll get it. That happened to me when I was studying biology. So I'm really looking forward now to talking to Dr. Humphreys. There's just no way I could understand his paper without him walking me through it. One reason I do this is, like I said, the best way to learn is to teach. And as I'm trying to teach my misunderstandings, I'm seeing what I'm misunderstanding. He could set me right. I would like to have the privilege one time of actually teaching what he's trying to teach in this paper, kind of more in my own words and elaborating and working through the math examples, etc. And then I'll understand what the issues really are. I'll have to ask him, quite a number of questions. But let me just read through a page and a half, and then we'll call it timeout, a pause, and then we'll wait for Dr. Humphreys to come on board. This is, I'm trying to. I'm really glad now that we had 3 nerd torture sessions on electromagnetic theory, because the next page is going to be heavy into it. Where this is the curl operator right here. And I'm going to have to ask him what these are. I think these are expectation values. Oh boy, so equation 9a, I'm going to have to ask him what equation 9a is. And I'm just going to embarrass myself. Some of the basics I don't know. Dr. Humphreys worked with, he lived electromagnetism. So some of this just seems probably trivial to him. Anyway, Let me just read another page and a half. The turbulent heart of dynamo theory. Kinematic dynamos. I'm sorry. Let me get this going here. Kinematic dynamos. Responding to the proofs that axis symmetric dynamos can't work, theorists began trying models without such symmetry. One broad class of those. Okay, I need to ask why. Okay, it fails according to Cowling's theorem. That actually is surprising. Theorists began trying to model without such symmetry. One broad class of those were the kinematic dynamos. Theorists tried to find specific large-scale core fluid flows that would produce the observed field. So these core fluid flows, core fluid flows. So would this be like we have a storm and you have all this motion being generated because there's heat energy, kind of like a storm? I'm going to ask him that. Okay. Kinematic, it's called kinematic dynamos. Kinematic dynamos. So we have a kinematic dynamo, and then we have a self-exciting dynamo, a Larmor. God bless you, Dr. Humphreys. This is so hard. This got me beat, man. You know, debating evolutionists is easy compared to this. In science's, to quote Jerry Coyne, in science's pecking order, evolutionary biology lurks somewhere near the bottom, far closer to the pseudoscience of phrenology than to physics. This is why physics is at the top of science's pecking order. It's good stuff, but it is also really hard. Yeah, this is kicking my rear end. Oh, this is hard. Biology was never this hard. Okay. Kinematic dynamos. Theorists tried to find specific large-scale core fluid flows that produce the observed fields. Bullard and Gelman used an infinite series of spherical harmonic fluctuations to describe the motions. The motions, though mathematically regular, were very complex. The series appeared to give a solution for the fields when truncated at the 12th harmonic. Because it was the first dynamo model to produce numerical results, it became very influential. However, later examinations showed that the infinite series does not converge, invalidating the solution. Other variations using different initial flows have failed to get around the problem. The only kinematic dynamos that appear to work, on paper at least, are existence theorems that have unrealistic geometries, such as infinitely large conducting medium. Apparently none have been found for spherical geometries like the Earth's core. Oh boy, let me try to uncoil this. And I could get this totally wrong. When you have a heat source and you have fluid, you can get, like what you see with the Earth's atmosphere, you get all the motions. And I think they're trying to come up with some way you can get motions. Now, people that know Fourier transforms, you can curve fit and find all sorts of interesting things if you isolate kind of one component of a flow, and that's not really very exact, guys. I'm sorry. and you can actually see things that aren't there. A good example is someone tried to use Fourier analysis on the stock market. He came up with all these, he decomposed it into 3 components for historical data, and he thought it was going to predict the future. It didn't. You just had to come up with different sets of Fourier components. You can just take Fourier analysis on to noise. You can get some interesting things if you have a small sample size. And I think this is what it's talking about when they talk about the 12th harmonic, that you're getting these complex flows and you're trying to extract a little bit of motion that's kind of unified so you can get a magnetic field versus nothing. And Russell Humphreys was pointing out later examination showed the infinite series does not converge. That means it's just noise. Doesn't for the same reason you can't use Fourier analysis on the stock market. Other variations using different initial flows have failed to get around the problem. The only kinematic dynamos that appear to work, on paper at least, are extensive theorems that have unrealistic geometry, such as an infinitely large conducting medium. Apparently none have been found for spherical geometries like the Earth's core. Man, we talk about some tough geophysics. Turbulent dynamos. Nearly 50 years after publishing the first anti-dynamo theorem, Thomas Cowling published a concise and useful review of the status of dynamo theory in 1981. His review boils down to the status of mean field electrodynamics. This approach divides fields and velocities into mean, average, and fluctuating turbulent parts. Then the theorist puts that equation template onto the foundational equation of dynamo theory, the magnetic induction equation. I need to review what a magnetic induction equation is. I don't know anymore what the magnetic induction equation is. Electromagnetic theory is hard, guys. Making the reasonable assumption that the turbulence is the same in all directions, isotropic, Cowling repeats the demonstration that throughout the field, the mean electric field E, bold font means vector, depends on the mean magnetic field B. E depends on B. Is this a chicken and egg problem? E depends on B and B depends on E. It's just, can't get one without the other. We'll see. Okay. And the formula describing that relationship is there, equation 8. That looks like Cowling's theorem, I think. All right, let's go back here. I want to look at the notes here. Most solids are somewhat conductive at high temperatures of the mantle. Most solids, doesn't have to be iron then. Another class of dynamos uses the assumption of geostrophic balance between the Coriolis force and the pressure gradients, but the assumptions appear to be unrealistic for the Earth, and the models appear to have other serious problems. Geostrophic balance. A geostrophic balanced dynamo. Electromagnetic induction is the creation of electromotive force by way of moving a magnetic field around an electrical conductor, and conversely the creation of current by moving an electric conductor through a static magnetic field. Electromagnetic induction is the creation of electromotive force by way of moving a magnetic field around an electric conductor. Okay, so the magnetic induction equation. So generator, you're moving the wires around a magnetic field, and that generates electricity. So if you have a permanent magnet, you can move the wire around the permanent magnet. It's going to create electromotive force. It's going to create a voltage generator. And thank you for looking that up, Mark. But there's an equation associated with it, and I think it's Faraday's laws of induction. That's the third equation of Maxwell's equations. And I could totally blow this, but let's just, while we're being nerd torture, Maxwell's equations. Okay, let's see. The Maxwell-Faraday equation, Faraday's laws of induction. Let's see if we have it here. The curl of E equals the change in B. The curl of the electric field equals the change in the magnetic field. And let's look at Maxwell's equations. Maxwell. Let's see if we see it here. Maxwell's equations. Oh, come on, give me the equations. There it is. Faraday's law of induction right here. I think that's the induction equation here. So in the show earlier today, we did the show on the curl. And so now we're really seeing the importance of this curl. And so thank you, Mark. So that's a third of Maxwell's equations. The changing B field implies a curl in the electric field. How can you get a curl of an electric field? This is interesting. Oh, well, okay. So I think in Humphrey's paper, it's referring to this equation. Let me see. When Dr. Humphreys comes on, okay, let's go to Dr. Humphrey's paper. So that would be, where did I see it? Where did induction come? Induction. Where did I see the induction equation? Oh, here it is. The magnetic induction equation in turbulent dynamos. Okay. The magnetic induction equation. It's a turbulent dynamo. So the magnetic So is that the magnetic induction equation? Is that the same one as, is this the magnetic induction equation right there? So that's what I'm going to ask Dr. Humphreys. Okay. The foundational equation of the magnetic induction equation. So the foundation of the dynamo theory is the foundational equation of dynamo theory is the magnetic induction equation. So this is going to be important. I'm going to ask Russell Humphreys, is this the heart of dynamo theory right here, this equation? Now I'm really glad I spent time studying the curl. Mark Connell says no. He said it's here. Okay. Okay, this is the, I think, let's see, where were we? Didn't mean to go there. So that is E d phi b dt. I want to take a look at it. Let's see. Man, there's so many versions of this. I think we can relate. I think this is the more general form. I'm just going to ask Dr. Humphreys. He lives, sleeps, breathes, and eats electromagnetism. So he's just the right guy to answer this. Gosh, I can't believe that I'm this lucky to have Dr. Humphreys willing to give so much of his time. I got to tell you guys, for you electrical engineering physics nerds, this is great stuff. You know, it's really hard to get, when I was in school, it's hard to get this much time where a professor would really just spoon feed you the stuff. What Dr. Humphreys can do, and I found this, and some of you probably understand this, a 5-minute conversation could actually save you 3 months work, because you're trying to figure out what one term means. And it's just great when someone can come along and save you months, if not years of work with a 5-minute conversation. I kid you not. It's just great. And so this is gold, guys, that Russell Humphreys. If I had to read this paper and try to understand it from scratch without having access to the author, it'd be killing me. This is just fabulous that there's someone there to kind of hold your hand and get you through it. Because I got to tell you, the biology papers were easier to read. You could just Google. If you saw a term and you didn't understand it, you could Google. And you weren't tied up with all the math. A lot of it was straightforward enough. You could get through it. It was just a lot of stuff, but it wasn't so interconnected, you know. It's more like just kind of knowing just a bunch of facts that don't necessarily depend on each other. Physics is so hard. Okay, so Cowling repeats the demonstration throughout the field, the mean electric field, E, bold font means vector, depends on the mean magnetic field, B. And then he gives this equation 8. Now let me look up Cowling's theorem, and we won't call it a day, we'll call it the end of the show. Cowling's theorem. See what it looked like. Cowling's theorem. Let's see an image of Cowling's theorem. Man, I wish they'd make these things bigger. I mean, this is terrible. Look how blurry that is. I don't see any cross products. Okay, that isn't Cowling's theorem. All right, at least we tried. Where A and B depend on fluctuating turbulent parts of U of the fluid velocity that lasts for a limited time, tau. Okay, so I need to ask what this is here. Equation 9b. Is this an expectation value? So what I mean is, what is this bracket here? Is that an average? Is that mean? Or is that an expected value? This isn't a normal parentheses, guys. It's some sort of bracket. And I need to ask that. So this is plenty to bother Dr. Humphreys with. This is gold. And I'm going to just pause here. I'm just going to end the show here. And I'm going to review my notes and also get ready to receive Dr. Humphrey connection. And I'll be monitoring my phone. Guys, thank you for helping me bear my cross as I study this. This will help us collectively to prosecute the creationist case. Just in review briefly, I think the big deal is going to be the doomsday equation of 5. Equation 5. I'm going to ask him, Dr. Humphrey says, equation 5, can I kind of call that the doomsday equation, that the Earth's magnetic field is going to decay in 1600 years? Is that why Wikipedia says it's going to decay in 1600 years? So that equation was formulated by Thomas Barnes. That's not, but I mean, it looks an awful lot like the equation in Wikipedia. And until we know it generates the Earth's magnetic field, it's really all speculation. They're just saying it was around for millions of years, but we have measurements in the last 120 years, and we still don't know what makes that magnetic field. how can we make predictions of where it's going? We can't just say, well, it's been around for millions of years, therefore it's not a problem. It's like, well, you're assuming that the millions of years is right to begin with. It's assuming the hypothesis you're actually trying to prove. That's circular reasoning. So this is going to be interesting. I need to just pause a little bit, just recover. My poor brain is burning out, and just review all the questions I need to review with Dr. Humphreys. Some of you, you're invited to join the next stream that'll be on this channel. It will be, God willing, with Dr. Humphreys. So in the meantime, take care, glory and honor to our Lord and Savior. This is why we are doing this, to honor him. And so I'll just close with the usual, and some Rachmaninoff's 18th variation on a theme of Paganini. Take care, and the Lord richly bless you.